we're going to continue to look at a couple of more implicit differentiation problems. And so the first one we're going to look at here is we hopefully have something that looks familiar to you. X squared plus y squared equals 25. If we were to think about that, that is the graph of a circle. So if we were to graph that, it is a circle centered at the origin with a radius of 5 squared, with a radius of 5. So if you were to think about graphing this, then, turn that off, sorry, just roughly have this kind of mental picture of what we have going on here. So, a basic example of where we have something where clearly y is not a function of x, right? It fails the vertical line test. And we are going to look for the equation of the tangent line or lines at x equals 3. So having a mental picture of the graph is kind of useful because we should be able to see that there are 2 points, and this is not a good looking circle here, especially down in quadrant 4. But if we were to think about what's happening at x equals 3, there are 2 different points on that circle at x equals 3. So we are going to end up with 2 different tangent lines. So because we can kind of wrap our mind around this particular graph, it kind of makes it a little useful, I think, in terms of the predicting about what's going to happen here. All right, so let's go ahead and realize maybe I hadn't drawn that picture and just recognize the initial things we always say, which is if I'm going to find an equation of a tangent line, I'm going to need the slope of the tangent line, and the slope of the tangent line means I'm going to need dy dx. So in this situation, we're going to say, all right, we're going to apply our implicit differentiation process, and we start that by taking the derivative of both sides with respect to x. So the derivative of x squared, of course, is just 2x. The derivative of y squared is 2y. Treating y as a function of x, we multiply by a factor of dy dx. That's the key with implicit differentiation that we've talked about. And then that, of course, equals derivative of 25 is 0. So we can get a pretty nice dy dx here. This one's pretty nice and quick to solve for. So as we look at solving for our dy dx here, we would just subtract over our 2x, and then we're going to just be able to divide both sides by the 2y. So we have a nice form here to work with on our dy dx. So my derivative dy dx, 2's reduce, we have negative x over y. So this is going to allow me to get the slope of the tangent line at x equals 3. But we realize this is kind of a different thing that doesn't happen with when we do explicit differentiation, which is that our derivative is in terms of x and y. So I'm going to need the y coordinate too. And this would be where normally we don't need the y coordinate until we get to the point where we are trying to figure out the equation of the line. Here we need it to even find the slope of the line. So let's actually just start by subbing in 3 into the original equation. So we would have 9, 3 squared 9, plus y squared is equal to 25. And of course, subtracting your 9, you have that your y squared is equal to 16. And then just remembering that anytime you're going to take a square root to get rid of a square, you have to remember to introduce the plus or minus square root. So if you didn't remember that and you weren't looking at the graph, then you could miss an equation. If you hadn't graphed it, but you remembered when you take the square root, you introduce the plus or minus, then you'd be okay. So this is now telling me I have 2 points which we can confirm graphically. I have 3, 4, and I have the point, and mine are definitely not drawn to scale, 3, negative 4. So I have 2 different points that correspond to x equals 3. I'm so sorry. this is the joy of working from home, recording videos. Sorry. You may have heard my dog in a previous video make his appearance, and right now there are people working outside at my neighbor's house, and every time he hears something, he feels the need to alert me as well, and you. Okay, so let's continue. Hope this goes okay. So now we need to find the slope of the tangent line at these two different points. So we really have kind of a branching here that's occurring because we're going to have two different equations. So let's just say we're going to find, maybe even kind of write this out here. So we're going to have the equation at the point 3, 4. So that's going to be one of the equations we need to find. And then we're also going to need to find the equation at 3, -4. So I'll just kind of branch these separately. All right, so as we do that, so here is then the slope of my tangent line evaluated at 3, 4 is going to equal, going back to my derivative, negative x over y, so -3/4 is the slope. And then, of course, the equation of my line, just y minus 4, equals the -3/4 quantity x minus 3. And you could leave it like that. You could certainly distribute through, if we just wanted to add the 4, even without distributing and combining like terms, you could maybe just leave it like this also. So I didn't say it had to be in slope-intercept, so I'm just going to leave it like that for this one. All right, let's do slope of tangent line evaluated. So our second line here at 3, -4. So negative x over y, so -3 over -4 is going to give us positive 3/4 on that slope. And so now y minus the -4 takes us to y plus 4 equals positive 3/4 quantity x minus 3. And again, maybe I'll just leave it essentially in the same way. I'll just subtract that 4 over to the other side. So there's two of those equations of those lines at x equals 3. All right, now let's do a part B. So what else might you be asked to do? All the classics: find dy dx, find equations of tangent lines, slopes of tangent lines, equations of tangent lines, maybe find a second derivative. So let's do that one here. So let's say we're also asked with this one to find our second derivative. And typically it will say something like in terms of x and y. And that's what we've been seeing, that the implicit differentiation typically gives us a derivative in terms of x and y. All right, so essentially I'm working off of, from part A up there, we had that dy dx is equal to this negative x over y. And now I am taking the derivative with respect to x. And so that's kind of where we get our notation on the left-hand side for the second derivative, that notation that kind of just looks like how I wrote the problem, the d squared y over dx squared. But that's really kind of where that notation comes from as you look at that left-hand side there. All right, taking the derivative on the right-hand side with respect to x, following the same rules as before. So we're going to start with our denominator left alone. I'm going to kind of lump that negative in with the numerator. So times the derivative of the numerator is -1 minus the numerator left alone, negative x, times the derivative of the denominator. Well, the derivative of y is 1, if you want to write that. You just differentiated a y, so once again, that's my implicit differentiation important action there. Multiply, introduce a factor of dy dx. And then this is all over the denominator squared. So the main reason that I said to you a lot of these problems are going to say, and if not, I would say be able to, if it's a second derivative, they may say, I would say, find that in terms of x and y, meaning we should be able to express that derivative as, if we go back up here, so this was my dy dx, negative x over y. Well, I can replace that dy dx. If they want this second derivative in terms of x and y, I can replace that second derivative with the negative x over y. And so technically this would be correct. Let's just get into the habit though of doing and getting better at, I hope, a little bit of simplifying. So I like to simplify complex fractions typically. I like to, especially when there's just one little mini denominator there, I a lot of times like to just multiply by a big version of 1, that is that little mini denominator over itself. Of course, that means I'm going to need to distribute the y through to both terms in that numerator. So I now have my second derivative here is looking like negative y squared minus x squared, because the y's have reduced, all over y cubed. So that's a pretty darn good looking form of the second derivative. But something really kind of neat happens with this particular example. We can actually factor out the negative in the numerator, and when I do, both the x squared and the y squared term become positive. I have reordered them, but that's just to make it look a little nicer. So negative quantity x squared plus y squared. And guess what? That negative x squared plus y squared, in particular the x squared plus y squared, this, if we go all the way back up to the original problem, x squared plus y squared, that equals 25. So we can actually, in this problem, this won't always happen, of course, but we get a really neat simplification that happens here, in that we can replace that quantity of x squared plus y squared, we can replace that with 5 by the original equation that we're able to do that. That's where that 5 came from. So here's a really simplified form here of my second derivative. They won't all be that nice, but that one sure did simplify nicely. Okay, let's take a look at maybe one more example here in this video. Number 2, I'm going to pull something actually from your homework. And this one we're going to have a trig function. It's good, right? Revisit a trig function. So suppose I have y equals, and this one's going to be tangent of 8x minus 6y. And again here we're just finding dy dx. All right, so this is another good example of a situation where there's no way I can solve this for y to get at y explicitly as a function of x. No way. So we need our implicit differentiation process in order to be able to find dy dx. So we start by saying, okay, let's say I'm going to just denote what I'm about to do, which is to take the derivative of both sides with respect to x. All right, on the left-hand side, derivative of y is 1. I just differentiated y, so I multiply by dy dx. So if you think about that, in some ways, every time we've been taking a derivative of y and calling it dy dx, it's kind of like doing this implicit differentiation process. All right, on the right-hand side, the outermost function, this is going to be a big old chain rule situation. The outer function is tangent. So the derivative of tangent is going to be secant squared with the inside function left alone. And now we need to take the derivative of that inside function. So that's the inside function left alone there. And then times the derivative of that inside function. Derivative of 8x is 8 minus 6 derivative of y. I just differentiated a y, so dy dx. And so here's what I now have. And my goal is to try to get dy dx on one side. So here's something you can't do right now, and I hope you wouldn't be tempted to do, which is you can't add the 60y dx over to the other side, because it is in this set of parentheses right now. It's protected. Okay, you can't get into it right now because it's in these parentheses. So the only way I can really get into it, I need to get it out of those parentheses. So you have a couple of options to do that. I suppose you could divide by secant squared, and then you just have the 8 minus 6 dy dx. So that would be one way to go. Another way to go would be to distribute through this secant squared. So there's a couple of different options here. So you could certainly think about saying, okay, if I need to get into that set of parentheses, how do I get something out of parentheses? And I think this is probably the instinct of most students, is when they see parentheses, is to distribute. So that's what I'm going to start with here. So let's just go ahead and do that. So we'd have 8 secant squared of 8x minus 6y, and then minus 6 secant squared of 8x minus 6y, and then times my dy dx. So it's out of those parentheses, and so now we can add it to the left-hand side. So now we can add, again, some of this is just a pain in terms of writing it out, and if you can see, just adding this to the left, you don't need to write this addition that I'm doing here. So adding the secant squared of 8x minus 6y times the dy dx, that's all one term, so adding that to the left-hand side. All right, so by doing that, of course, I now have my two terms with the dy dx over here on the left-hand side. I have the dy dx term, like a 1 dy dx, and I now have my 6 secant squared 8x minus 6y dy dx term also over on the left-hand side. And so my last step, maybe second to last step, is the whole reason that we do this is really so we can factor out this dy dx from both terms here. So we're going to factor out this dy dx, and when we do, we would have times the quantity of 1 plus that secant squared of 8x minus 6y term there. And again, the reason we factor it out is now we have it times something, and that means that we can do the opposite, of course, and just divide by that big old binomial. So some of these problems, their bark is worse than their bite. Thinking of my dog barking here. In that a lot of the algebra isn't as bad as it looks. It's in some ways just a lot of handwriting here, rewriting these kind of lengthier looking functions. And so there's my dy dx here. So dy dx could be written as 8 secant squared of 8x minus 6y all over 1 plus 6 secant squared of 8x minus 6y. And you definitely can't reduce anything there because of the addition in the denominator. Now, your other option would have been, at this step up here, if you wanted, you could have said, well, what about if my goal is to get into that set of parentheses? How about I just divide by that quantity that is in front of that set of parentheses? So you could have went with that. You could have said, I am just going to divide both sides by my secant squared of 8x minus 6y. So I'm going to divide by secant squared of 8x minus 6y. Now, if it was me, I would probably write that left-hand side rather than dy dx divided by something. And since it's secant, 1 over secant is really cosine. So I probably would, at that step, it would look a lot nicer to write this as cosine squared dy dx. And then on the right-hand side, you just have your 8 minus 6 dy dx. And so now you can add that 6 dy dx term over to the left-hand side. And then you're going to now have your 2 dy dx terms on the left-hand side. And by doing that, of course, we're going to get to do the factoring out of our dy dx. So on the left-hand side, I now have two terms that have a dy dx in them. And so I am going to factor out my dy dx. And when I do that, I would have cosine squared 8x minus 6y plus 6 in parentheses. And my last step is going to involve dividing then by that big old binomial, the cosine squared of 8x minus 6y plus 6. So divided by cosine squared, 8x minus 6y plus 6. So here is a different looking form of your dy dx. So dy dx is equal to 8 over cosine squared of 8x minus 6y plus 6. Now, we could definitely show that these two are equal to each other. And what would that involve? I would say just thinking about 8 secant squared as being over cosine squared of 8x minus 6y. And I'm not going to go through this just in the interest of time. But if I wanted to really convince you, which you can see I kind of do because I'm having a hard time stopping myself, I would rewrite each of those that way. And then if you multiply to clear that little mini denominator, like I like to do, multiplying by cosine squared of that quantity over itself, and then distributing that through, you're going to get to exactly the form you have on the right-hand side. So the first method is the one I wrote because I think students, if they have to get something out of parentheses, they automatically think distribute, and that's A-okay. I'll be honest, I kind of like the one on the right a little bit better, but both of them obviously give us equivalent forms of the same answer. So next time when we come back, we're going to look at the power rule. Yeah, I know, again, right? But the book kind of rolls out showing the power rule first with positive integers, then with negative integers. With the quotient rule, we proved that. And now we're going to be able to prove it with rational powers, meaning fractional exponents, if you will, using implicit differentiation. So we'll take a look at that next time.